Hello everyone, and welcome to some more remote learning. Today we're going to go over some more Calculus 2, and we're going to jump into parametric equations. So this is a little bit of an introduction, and we're going to jump right into it. So in example 1, it says to sketch the parametric curve for y equals t squared plus 1 and x equals t over 3 for negative 3 is less than or equal to t, which is less than or equal to 3. By making a table, so we're going to do this by making a table of x and y corresponding to the different values of t. And then once we graph that, we'll draw arrows to indicate the direction of the curve. Now usually we've been dealing with y equal to some function of x, where x is that variable that dictates what y is equal to. However, now we have y as some function of t and x also as a function of t. So as opposed to having y equaling f of x, now we have y equaling some function of t, f of t, and x equaling some function of t, g of t. But let's start by making that table to show you how t affects x and y. So here I'm going to have t, then I'm going to do x values, and then I'm going to do y values. Now for my graph though, I want that to just be my usual xy coordinate system. So let me go ahead and graph that. All right, let's start with a t value of negative 3. And then we'll do a t value of negative 2, negative 1, 0, 1, 2, and 3. So note when we plug in negative 3 for t, negative 3 over 3, looking at the equation for x, negative 3 over 3 is going to be a negative 1. So we'll get negative 1 in the x. And what do we get in the y? Plugging in a negative 3, we get negative 3, that quantity squared, which becomes a positive 9, plus 1, which is equal to a positive 10. So I'm going to go ahead and graph that on my xy coordinate system. This will be, let's make this 1/2, 1, 1/2, 1. So this is negative 1/2, this is negative 1, this is a positive 1/2, and this is 1. And then I'll count by 2s. 2, 4, 6, 8. This will be 10. And then negative 2, negative 4, negative 6, negative 8, negative 10. So that's a scale I'll go ahead and use. So when I graph negative 1, 10, I'm at this point here, negative 1 in the x and 10 in the y. Now let's plug in negative 2 for t. Plugging in negative 2 for t, we'll get negative 2/3 for x, and for y, negative 2 squared is a positive 4 plus 1, which is 5. So graphing that, negative 2/3 falls about here, and then 5 will fall roughly here. Next, plugging in 1, that's negative 1/3, and plugging in 1, negative 1 squared is 1, plus 1 is a positive 2. So when I'm at negative 1/3, I'm at 2. And then plugging in 0, that gives us 0 for x, plugging in 0 for t, 0 squared plus 1, that's 1 for y. So then we're at 0, 1. Now plugging in 1, I'll go ahead and do my x coordinates for the rest of these. We'll have 1/3, 2/3, and then 3/3, which is positive 1. And now I'll go ahead and solve for my y's. So when I plug in 1, 1 squared plus 1 is 2. 2 squared plus 1 when I'm plugging in 2 gives me 5. And 3 squared plus 1 when I'm plugging in a positive 3 for t is 10. Now I know I did those last few coordinates fairly quickly, but it's the same concept as when we did those negative numbers. So when we're at 1/3 in the x, we're at 2 in the y. When we're at 2/3 in the x, we're at 5 in y. And when we're at 3 for t, which gives us 1 in the x, we are 10 in the y. And if I was to connect those, what do we have? We have something that resembles a parabola. Now our last step was to draw arrows to indicate the direction of the curve, which I'll draw in red. So to get the direction of the curve, we're going to start at our lower bound for t, which is -3, and work our way to our upper bound. That's that direction of the curve, which, remember, we started with plotting this point for -3. So our direction, drawing my arrows, would be from that leftmost point going towards that rightmost point. Now, just to make you think a little bit more about direction, because that seems rather simple in this problem, negatives to positives, think about if I took this x equals t over 3 and changed it to be x equals -t over 3. Then, when I plugged in my t values, my x's that were negative would now become positive, and my x's that were positive would now become negative. So starting at that -3 value for t, my first point for x with this new formula would have started at the right. So my direction, if this was my x, would have been the opposite direction. That's why it's not necessarily always starting from the left and moving from the right. It depends on how you plot those points, starting at your lower bound of t and making your way towards your upper bound. Now, I'm going to show you a little bit of an easier way to figure out what exactly these parametric equations look like for x and y. And this is now going to be by eliminating the parameter to obtain the equation in x and y. And how we eliminate that parameter is we're simply going to solve for t, either using x or using y. We'll solve for t and then plug that t value into our other equation so that it's in terms of x and y. So for example, if I take this x equal to the square root of t plus 1, I'll solve for t. So if I square both sides, I get x squared equals t plus 1. But remember, I want to solve for t so that I can plug it in over here. I'm going to subtract 1 to get that t is equal to x squared minus 1. Now for y, I no longer have y equals to minus t. I'm going to plug x squared minus 1 in for that t. So this is going to be minus x squared minus 1. And those parentheses are important because x squared minus 1 represents t, and we're subtracting all of t. So y is going to be 2 minus x squared minus a -1, so that will be 3 minus x squared. Which, this is a lot easier to visualize when we go to graph. Because think about it, my y-intercept is going to be 3, and that's a parabola that opens down. However, this is not quite our curve because our curve is restricted with our t values. So the lowest t value we have is a -1, and the greatest t value we have is a +3. So before I get crazy and graph this, let's go ahead and find our end bounds. So if I plugged in -1, I'll go ahead and plug it in for t in my x equation. X equals the square root of -1 plus 1, that's x equals the square root of 0, which is 0. So I'm actually starting at x equals 0. So I'm starting at my y-intercept. Now I'll plug in 3 to see where I'm ending. If I plug in 3 for t in my x equation, I'll get x equals the square root of 3 plus 1, which x equals the square root of 4, which is a +2. So I'm ending at x equals 2. However, I don't know what that y value is exactly right off the top of my head, so there's two ways to figure it out. We can either plug 3 in for t, which we get 2 minus 3, which is going to be -1, or I could have plugged that value of 2 that I already solved for in my x into my y equals x equation. 3 minus 2 squared would be 3 minus 4, which is indeed that -1. And because I know this looks like a parabola, I'll go ahead and connect those dots. So there's my function graphed and my direction. Remember, we started when x was 0 and went until x was 2. So my direction, again, is going from the left to the right. So knowing this method, let's go back up to number 1 and double check real quick. I have x equals t over 3 and y equals t squared plus 1. So if I solve for t, I'll use x equals t over 3 to solve for t. That'll be that 3x equals t. Then all I have to do is plug in 3x in for t in my y equation. So y equals 3x, that entire quantity, squared plus 1, which gives me y equals 9x squared plus 1, which is this parabola pictured. When x is 0, we get our y-intercept of 1, and when x is 1, we get 10. When x is negative 1, we get 10 as well. So you can see that we also could have solved this way and then just found xy points. Now let's continue on to something I think is a little bit trickier to eliminate. X equals the cosine of t and y equals sine of t. If at this point we attempted to solve for t, right away you would probably be thinking, okay, so if I took the inverse cosine of x, that would be equal to t. So then y is going to equal the sine of the inverse cosine of x. But how in the world does this help me? I can't picture the sine of the inverse of another trig function. So this is where we're going to use some Pythagorean identities to help us out. And now one that's really important in this case is the fact that cosine squared of some value, theta, plus the sine squared of that same value equals 1. So if I have that x equals cosine of t and y equals sine of t, well, if I squared both of them, that would be that x squared equals the cosine squared of t and y squared equals sine squared t. Are you seeing what I'm seeing? There's my x squared, there's my y squared. So for this case, I have that x squared plus y squared equals 1, which this is an equation of a circle with a radius of 1 because our circle equations are in the form of x squared plus y squared equals r squared. So our radius for our circle is 1, and because there's no shifting in this x or y, we're also centered at the point 0, 0. So if I was to draw, here is my circle with a radius of 1. However, remember, we have to make sure to check our t values because t is only going from 0 to pi. So because t goes from 0 to pi, think about it. Plugging in 0 for t, cosine of 0, I'm starting at 1 in the x, and then cosine of pi is a negative 1. So I'm actually only going to have half of that circle. And that direction is counterclockwise because I'm starting at this x value and moving to this x value. Now just to think about this, give you a little bit of practice, how would I get a full circle out of this? Well, right off the bat, there's two different ways I see. I can easily change my bounds going from 0 to 2 pi, because then if I went from 0 to 2 pi, I'm starting at a cosine value of 1 and going all the way around to another cosine value of 1. But that's not the only way I could get that full circle. I could also switch what's within my functions themselves. So I could do the cosine of 2t and the sine of 2t. Because then think about it, when I'm plugging in 0, I still get the cosine of 0, but then when I plug in pi, I get the cosine of 2 pi, which gives me all the way back around. So you can see you can manipulate your parametric equations and what that graph looks like by either increasing or manipulating your t-bounds or changing the values within your x and y functions. So now on your own, I want you to think of a way to reverse this direction. If we're starting at x equals cosine of t and y equals sine of t, how do I actually start from this point on the left side and move to the point on the right side. Go ahead and give that a go and leave it in the comments below once you figure it out. For now, let's move on to our next page. So now is when we're really getting into these parametric circles. I introduced it in the example above, but now we're really going to talk about it. So we're going to graph the parametric equations for x equals -3 cosine of t and y equals -3 sine of t for 0 to 2 pi by eliminating the parameters and finding the description of that circle or the circular arc in terms of x and y. And then we're going to give the center and the radius, and we're going to indicate positive orientation, which we did those three things above in example B without even realizing what we were doing. Now remember, what's that identity that helps me out here? It's going to be the cosine squared of theta plus sine squared of theta equals 1. So I'm going to try to manipulate these so I can get a cosine squared and a sine squared. I think one of the easiest ways to do that is to isolate my cosine and sine. So I'm going to write x as, I'll divide by my -3 to get cosine of t all by itself, and I'll do the same for y. I'll divide by that -3 to get sine of t all by itself. Now all I have to do is square both sides to get my cosine squared and my sine squared. So this is going to be x over -3 squared is going to be x squared over 9, and then that's going to be added to y squared over 9, and that's equal to 1. Now I'm not quite in that nice circle formula, x squared plus y squared equals r squared, but I can get there by multiplying both sides by 9. If I do that, I'll have x squared plus y squared equals 9. So here's my circle. I'm not shifting x and y at all, so I'm going to be centered at 0, 0. So my center is 0, 0. My radius, my r squared, is equal to 9, which means that my radius is equal to the square root of 9, which is 3. And now I just have to indicate positive orientation, which this is when our t value really starts to come into play to help dictate how we're moving around this curve. So I know I'm going to have a circle with a radius of 3. Now I just have to figure out exactly where I'm stopping and where I'm starting. So if I'm plugging in 0 for t, I'm going to have the cosine of 0, which is 1, and 1 times -3 is going to be a -3. So I knew my radius was going to be 3, so I knew I was going to either be at 3 or -3 on that x-axis when I intercepted it, because the sine of 0 is just 0. But I'm actually starting at this point -3 in my x. And if you can think about 2 pi, plugging 2 pi in, I'm going to be at a positive 1 again. 1 times -3, I'm going to be right back at this point -3. However, I don't know if I went around to the right or if I went around to the left. All I know is I started and stopped at this point, so I definitely have that full circle. So what might be helpful is to plug in a number between 0 and 2 pi. If I plugged in a number halfway between, I'm going to guess that I'm going to get something halfway in between as well, which then I'm still confused. Am I going around clockwise or counterclockwise? So what I'm going to actually do is I'm going to plug in pi over 2. If I plug pi over 2 in for the cosine of t, the cosine of pi over 2 is 0. So I'm going to be at 0 on my x. So I'm going to be somewhere along that y-intercept. Now I'm going to plug in pi over 2 in for t to figure out, am I going to be positive for y or am I going to be negative for y? But plugging in that pi over 2, plugging it in for t, the sine of pi over 2 is a positive 1, but I'm multiplying it by a -3. So my next point will be here. And then I'll go to pi, which would give me this point here. 3 pi over 2 would give me this point here, and then 2 pi. So you can see that I am actually going counterclockwise around this circle. I'm just starting and stopping at this point on the left, and remember our radius is 3. Let's move on to example 4, really hitting this concept home. So in example 4, we're going to graph the parametric equations x equals 2 plus cosine of 2t and y equals 1 plus sine of 2t for 0 less than or equal to t, which is less than or equal to pi. Then we'll eliminate that parameter, find the center, radius, and again, indicate that positive orientation. So the easiest way to do this is isolate my cosine and my sine. And I like to start with that identity. Cosine squared of theta plus sine squared of theta equals 1. So my x minus 2 is going to be equal to cosine of 2t, and my y minus 1 is going to be equal to the sine of 2t. So now I've isolated my cosine and sine functions. I'll square both sides. So this will be x minus 2 squared equals cosine squared of 2t, and y minus 1 squared equals sine squared of 2t. So now that I have a cosine squared and a sine squared, I'll plug those on in. So x minus 2 squared plus y minus 1 squared equals a positive 1. So I still have some circle with a radius of 1, although I'm not sure if it's a full circle yet until I really use those t values. However, I'm no longer centered at 0, 0, because I'm shifted in the x direction and I'm shifted in the y direction. So before we really jump into this problem, I want to introduce you to just the general equation for a parametric circle, which is x, our function x, equals x naught plus a cosine of b times t, and y is going to be equal to y naught plus a times sine of bt, which we've seen up above in each of the cosine sine examples so far. So if I was to solve this out, subtracting x naught over and then dividing by a, or subtracting y naught over and then dividing by a, squaring both sides, plugging it in, I would get that x minus x naught squared, and that would be over a squared, plus y minus y naught squared, and again that's over a squared, equals 1. And again, that's just using that identity. However, I have an a squared in both my terms, so I'm going to get rid of them by multiplying a squared over x minus x naught squared plus y minus y naught squared equals a squared, where that a is my radius, and just remember that your radius is always going to be positive. So I'll write this as the absolute value of a in case we have some negatives up here. And b dictates my direction or my positive orientation of my curve when I go to draw my arrows. So if b is greater than 0, then the circle is generated counterclockwise, where if b is less than 0, then we're going to be generating it clockwise, which might be helpful for that task I mentioned earlier when how to reverse that direction in example 1 part B. And lastly, our center is now going to be x naught, y naught. In 2 of the examples we've already completed, x naught and y naught were both 0 because nothing was subtracted from x or y. However, now we have a bit of a shift for example 4. So my center, I know my radius is going to be 1 because that's my a. Squared is 1, so the square root of a squared is also 1, and my center is now 2, 1. Here's that x naught, here's that y naught, here's that x naught, here's that y naught. So either formula you can use to get that value. And looking at our b, because our b is positive, this is going to go in the counterclockwise direction. So now that we know that it's counterclockwise, this is going to be a little bit easier to graph, because now t will just really be to help us figure out where we're starting and stopping. So I know my center is at 2, 1, So here's the center of my circle, and I have a radius of 1, and I'm going to be starting and stopping at, well, let's take a look. Plugging in 0, cosine of 0 is 1, 1 plus 2 is 3, so when x is 3, remember with that radius of 1, I'm going to be here, and plugging in pi, cosine of 2 pi again is 1, 1 plus 2 gives me 3, so I'm going to be right back. And remember that direction B is positive, so we're moving counterclockwise. Now let's move on to our last page where we're going to go over parametric equations of a line or a line segment. Now we're going to consider parametric equations of the form of x equals x naught plus at and y equals y naught plus bt for negative infinity is less than t, which is less than infinity. So essentially that entire line. A line segment, we would have a specific finite starting and stopping point. When we go from negative infinity to infinity, we're getting that full line. So let's go ahead and find this equation of the curve by eliminating our parameters. And remember how we do that is we solve for t using one of our equations. I like to use my x equation and then plug it in for y, but you can use your y equation and then plug it in for x. I'm going to do x minus x naught equals a times t. So you can see all I did was subtract x naught. Now I'm going to divide by a to isolate my t. So I have x minus x naught over a equals t. So what I'm going to do is I'm going to plug what t is in for t in my y equation. So I'll get that y equals y naught plus b times the quantity x minus x naught all over a. Now if I simplified this down a bit, think about this. What if I did y minus y naught equals, if I combined my b and a, I'd get b over a times leaving x minus x naught in those parentheses. What does this look like? That's point slope form. Y minus y naught equals m times x minus x naught. So my slope is b over a. And my point, I have my x naught, I have my y naught. So I have a point and a slope. I can easily create a line. So let's do example 5. Considering this parametric equation, x equals 4 minus 3t and y equals negative 2 plus 6t, we're going to find the slope and a point on the line. Well, right away, remember, x naught plus a of t. So I know that my x naught is equal to 4 and my a is a negative 3. Y is y naught plus b times t. So my y naught is negative 2 and my b is a positive 6. So without even needing to eliminate any of my parameters, I'll know exactly what I have, because my point on my line is going to be x naught, y naught, which in this case is 4, negative 2, and my slope is b over a. So that's going to be 6 over negative 3, which gives me a negative 2. So there we have it. 4, negative 2 is a point on my line, and negative 2 is my slope. And if you want to double check to make sure 4, negative 2 is definitely a point on that line, think about what t value we would need for x to equal 4. We would need a t value of 0. So if I use that same t value of 0, I do indeed get that y equals negative 2. So when t is 0, that's that point on my line, and my slope is negative 2. So go ahead and try to come up with an example on your own, where you have a center of 1, 3, and a slope of a positive 5. So again, that's a center of 1, 3 and a slope of a positive 5. Now there's many different a's and b's you can use to get this slope of 5, but your center, those are your x naught, y naught values. But b and a, get creative, because 5 could be anything from 20 over 4 to 100 over 20. There are so many different ways to come up with that slope of 5. So have some fun and get creative and come up with your x equation and your y equation, those parametric equations. Now hopefully you found this video helpful and a good introduction with your lesson to parametric equations. In the next video, I'll go over some more examples where we start talking about how to take the derivatives of parametric equations. But this is going to be very helpful, especially when you move forward into Calc 3 or multivariable calculus. So definitely get used to parametric equations, writing x and y in terms of some other variable. So until next video, good luck with your studies.